In this module, we will look at decryption concepts, certificate management, SSL forward proxy decryption, SSL inbound inspection, and other decryption topics, including unsupported applications, no decryption, decryption port mirroring, hardware security modules, and troubleshooting SSL session terminations. Encrypted sessions can be used to insert malicious content or exfiltrate sensitive data. To better protect your organization, the firewall should be configured to decrypt and examine encrypted SSL, TLS, and SSH network traffic. For more information about the packet handling sequence inside of a PAN-OS device, see the Packet Flow Sequence in PAN-OS document, available on the Palo Alto Networks support website, live.paloaltonetworks.com/docs/doc1628. Decryption concepts. Each year, more web traffic is encrypted. Palo Alto Networks firewalls provide the capability to decrypt and inspect network traffic for visibility, control, and granular security. Decryption on a Palo Alto Networks firewall includes the capability to enforce security policy on decrypted traffic, where otherwise the encrypted traffic might not be blocked and shaped according to your configured security settings. Use decryption on a firewall to prevent malicious content from entering your network or sensitive content from leaving your network concealed as encrypted traffic. A Palo Alto Networks firewall can decrypt SSH v2 and SSL TLS inbound and outbound network traffic. The SSL TLS protocol encrypts an HTTPS connection between a client and a server where no pre-existing secure channel is present. SSL TLS is commonly referred to as just SSL. Initiation of an SSL session follows this basic flow. 1. A client requests an SSL connection. 2. The server responds with its certificate that contains its identity and public key. 3. The client uses the PKI to validate the server certificate and server's public key. 4. If the certificate is valid, the client uses the server's public key to encrypt a symmetric session key and send it to the server. 5. The server uses its private key to decrypt the session key. Both sides use the session key to encrypt communications. The communication partners periodically might need to establish a new session and re-key the communication. The process of re-keying new or existing sessions is known as perfect forward secrecy, or PFS, and provides assurances that if a private key is compromised, any recorded former sessions cannot be decrypted. PFS support for SSL forward proxy was added in PAN-OS 7.1. PFS support for SSL inbound inspection was added in PAN-OS 8.0. You can configure SSL forward proxy decryption on the firewall, which decrypts SSL traffic between an internal host and an external web server. In this configuration, the firewall acts as an SSL proxy. With SSL forward proxy, a connection is formed between an internal user and the firewall, while a separate but related SSL connection is formed between the firewall and the external web server. As an example of the usefulness of SSL forward proxy decryption, consider a scenario where an internal user will connect via an encrypted connection to Facebook. The company policy is to allow employees to read Facebook, but to prevent Facebook chat and Facebook posting. If SSL decryption is enabled for the Facebook application, company policy can be implemented easily with the firewall. If SSL decryption is not enabled, then the firewall cannot identify which application is inside the SSL connection. nor can it recognize that application shifts are occurring within the connection. You can also configure SSL inbound inspection decryption on the firewall, which decrypts SSL traffic coming from external users to internal users. To configure SSL inbound inspection, you must have access to the server's private key and certificate. In this configuration, the firewall does not act as an SSL proxy. An SSL connection is formed directly between the external user and the internal server. The firewall decrypts and only inspects the traffic flowing through it. The firewall can supply security policy and security profiles to the SSL connection and block disallowed traffic. You can configure SSH decryption, which can decrypt outbound and inbound SSH traffic. If an SSH tunnel, port forwarding, is discovered, the SSH connection is blocked to ensure that SSH is not being used to tunnel disallowed applications and content. You can also apply a decryption profile to your security policy rules to control normal, non-port forwarded SSH traffic. The public key infrastructure solves the problem of verifying the identity of a public key owner. PKI is the set of hardware, software, policies, and standards used to create, manage, distribute, and revoke public keys and digital certificates. A PKI digital certificate is a method of packaging and distributing public keys in such a way that proves the identity of their owners. Palo Alto Network's firewalls support X.509 format certificates. A PKI Certificate Authority, or CA, provides services that authenticate devices, services, and people by issuing the certificates that confirm their identity and public key. CAs are arranged in a hierarchical fashion similar to a file system. The root CAs form the top level of the hierarchy, and intermediate CAs form the second and lower levels. An intermediate CA is certified by a root CA to issue certificates or to certify additional lower-level intermediate CAs. Each CA has a certificate database that stores certificates, revokes certificates, stores certificate requests, and issues certificates. Devices use a certificate store to store their private keys and the certificates they have been issued. They also maintain a list of trusted CAs. This list of trusted CAs can be updated by a user or by a device software update. If the certificate of the issuing CA is not added to a client's certificate store, the client receives a warning message when browsing to secure sites verified by that CA. The certificate chain of trust is a hierarchical list of certificates used to authenticate a device, service, or person. In the example, the chain begins with the device's certificate. Each certificate in the chain is digitally signed by the entity identified by the next higher certificate in the chain. The chain terminates with a root CA certificate. The root CA certificate is always self-signed by the root CA itself. A root certificate is a self-signed certificate because the issuing authority is itself. These root CAs form the basis for all PKI deployments. The device can verify the owner of a public key as long as the device's list of trusted CAs includes a root CA in the chain of trust. For example, a browser can check to determine which authority issued an intermediary certificate, retrieve the intermediary's certificate from that higher authority, and verify the intermediary certificate. This process continues until a root CA is encountered in the chain. In practice, this process is rarely more than 2 or 3 hops. You can rely on a certificate and the information and public key it contains when the issuing CA is trusted and the signature hash value in a certificate is valid. An issuing CA computes a hash value for critical information in a certificate and includes that hash value in the certificate. The receiving entity can recompute and compare the hash value to ensure that a certificate has not been intercepted and altered by a malicious third party. To prevent tampering of the hash value and other critical information in the certificate, the issuing CA encrypts the information with its own private key. The receiving entity uses the issuing CA's public key to decrypt the information in order to recompute and compare the hash value. Because only the issuing CA knows its own private key, encrypting certificate information using its private key is essentially an act of digitally signing the certificate. If the certificate of the issuing CA is not added to a client's certificate store, the client receives a certificate warning message when browsing to secure websites verified by that CA. Palo Alto Network's firewalls use certificates for many purposes. This module describes the use of certificates for SSL TLS decryption of inbound and outbound network traffic. However, a firewall can use certificates for all of the other authentication functions listed. All certificates in the chain of trust must be checked before an SSL TLS connection can be considered secure. Before it can check the certificates, the SSL client must determine the chain of trust. Then the SSL client must validate each certificate in the chain. If the signatures are valid, then the SSL client must check the revocation status of each certificate in the chain. Two tools are available to check certificate revocation status. There are Certificate Revocation Lists, or CRLs, and the Online Certificate Status Protocol, or OCSP. A firewall can use CRL or OCSP to verify certificate revocation status for SSL decryption. Global Protect components, Captive Portal, IPsec VPNs, and MGT port access. A certificate might need to be invalidated before its expiration date because the certificate owner's private key might have been compromised, the host name or username of the certificate owner might change, a host could be retired or a user can leave the company, or a counterfeit key might need to be invalidated. The list of revoked certificates is stored on the CAs in their certificate database. Some devices, including a Palo Alto Networks firewall, can submit a certificate signing request, or CSR, to a CA. To submit a CSR, the device generates a public and private key pair and identity information, and then submits the public key and identity information to a CA using a CSR file. The CA uses the information in the CSR file to create a certificate signed with the CA's signature. The signed certificate is sent back to the device. The advantage of using CSRs is that the device becomes part of the existing PKI infrastructure and its certificate chain of trust. Another advantage is that the device's private key never leaves the device. The primary disadvantages are that the device must be capable of generating a CSR and that there is some administrative overhead compared to a device using a self-signed certificate. Certificate management. The web UI includes certificate management for the firewall at Device, Certificate Management, Certificates. Using the web UI, you can generate and view certificates or generate CSRs. You also can import certificates from a third party or internal CA and export certificates to other devices. You can also modify certificates to meet specific use requirements on the firewall. Certificates issued by the firewall also can be revoked using this interface. Each certificate is authorized for different uses. For example, a signing certificate is authorized to sign other certificates. A signing certificate must be a CA certificate. The firewall requires a signing certificate to support features such as SSL forward proxy or Global Protect. As you will see, there are 3 methods for obtaining a firewall CA certificate. Click each of the methods shown to learn more. To create a self-signed CA certificate in the web UI, be sure to leave the Signed By field blank and select Certificate Authority. The blank Signed By field indicates that this is a self-signed certificate. Selecting the Certificate Authority checkbox enables this certificate to be signing a certificate that can be used to sign other certificates. The common name can be the FQDN or IP address of the firewall, or a label that uniquely identifies the purpose of the certificate. Note that you also can configure an OCSP responder for each certificate. You also can change the cryptographic settings used to generate the certificate and add a variety of certificate attributes that are used to further identify the owner of the certificate. After you click Generate, the new certificate appears in the list of certificates in the Certificate Management interface. If you have an internal CA, then you can use it to help create the firewall's CA certificate. To create a public and private key and a CRS using the web UI, ensure that you select External Authority, or CSR, for the Signed By field. If the certificate will be a signing certificate capable of signing other certificates, then select the Certificate Authority checkbox. The common name must be the FQDN or IP address of the firewall. Note that although these fields are not shown in the example, you can also configure an OCSP responder for each certificate, change the cryptographic settings used to generate the certificate, and add a variety of certificate attributes that are used to further identify the owner of the certificate. After you have the form completed, click the Generate button. A new but unsigned certificate appears in the Certificate Management window. Select the checkbox of the new certificate in the Certificate Management interface and click Export to generate a .csr file. Send this .csr file to your internal CA. The internal CA will sign the certificate and then create a .pem file. Use the web UI to import the .pem file into the firewall. With a Firewall CA certificate in place, you can use the web UI to create any other required certificates, and they can be signed by the Firewall's CA certificate. A Firewall CA certificate and public and private key pair can be created on an internal CA and imported to the firewall. Ensure that you have a secure network because the firewall's private key will be transferred over the network. After the file containing the certificate and keys has been created by the internal CA, use the form shown here to import the files. A PKCS12 file contains both the certificate and private key in the same file. A PEM file containing the certificate will not contain the private key. The private key would have to be transferred in a separate file. With a Firewall CA certificate in place, you can use the web UI to create any other required certificates, and they can be signed by the Firewall's CA certificate. To help you manage certificates, PAN-OS software organizes the certificate listings as a hierarchical list. This format simplifies the process of determining which certificates are related by grouping certificates under their CA certificates on the system. In the example, an administrator is preparing to deploy a Global Protect environment. To enable certificates to correctly authenticate Global Protect components to each other, the same CA must issue all the certificates. The web UI display makes this check simple. SSL forward proxy decryption. Use an SSL forward proxy decryption policy to decrypt and inspect SSL TLS traffic from internal users to external web servers. SSL forward proxy decryption prevents malware concealed as SSL encrypted traffic from being introduced to your corporate network. It also helps to prevent the exfiltration of sensitive data. A firewall that is configured to decrypt SSL traffic going to an external web server functions as a forward proxy. In this scenario, the firewall intercepts the SSL client's request for the server certificate. The firewall then contacts the server and requests the server's certificate. The server responds to the firewall with its certificate, which the firewall verifies. The resulting secure SSL connection is between the firewall and the server. Then the firewall signs the server certificate with the firewall certificate and sends it to the SSL client. The SSL client verifies the firewall certificate that was used to sign the server certificate, and the result is another secure connection between the firewall and the SSL client. The SSL client uses the proxy connection to the server through the firewall. By default, the firewall dynamically chooses the key size to use to establish an SSL forward proxy session for a client, based on the key size used by the destination server. You can configure a static key size for SSL forward proxy sessions between the firewall and clients, regardless of the key size used by the destination server. Be aware of the following points when configuring and using SSL forward proxy. The validity date on the firewall certificate is taken from the validity date on the destination server certificate. The firewall acts as a proxy for the SSL connection, not the underlying traffic. Packet capture functionality executes before decryption, which means that a packet capture or PCAP file will contain encrypted data. With SSL forward proxy decryption, the firewall resides between the internal SSL client and external web server. As a trusted third party, the firewall uses its forward trust or forward untrust certificates to inform the SSL client whether the firewall has verified the validity of the web server certificate. When an SSL client initiates a session with an external server, the firewall intercepts the SSL request and forwards its own SSL request to the server. The server certificate is sent to the firewall. If the server certificate is signed by a CA that the firewall trusts, then the firewall creates a copy of the server certificate signed by the firewall's forward trust certificate. If the server certificate is signed by a CA that the firewall does not trust, the firewall creates a copy of the server certificate and signs it with its forward untrust certificate. In either case, the firewall sends the signed certificate to the SSL client. If a forward untrust certificate was used, the SSL client sees a block page warning that the website that it is trying to connect to is not trusted by the firewall that is acting as an SSL proxy. The user can choose to proceed or terminate the session. The first step to configure SSL forward proxy decryption is to configure a forward trust certificate on the firewall. The forward trust certificate can be signed by an internal CA or by a firewall CA. As an alternative, you can create a firewall self-signed forward trust certificate, but every SSL client will have to get this certificate installed in their certificate store. Otherwise, they will get certificate warning errors. Use the Certificate Management interface to create a firewall certificate to use as a forward trust certificate. In the example, the firewall forward trust certificate was signed by the CA from the internal CSR certificate, which is why it appears as a child of the CA from the internal CSR certificate. The CA from the internal CSR certificate is trusted by the SSL clients, which means that the clients will trust the firewall forward trust certificate. Click to open the certificate after it has been created and select the Forward Trust Certificate checkbox, which enables the firewall to use the certificate as its forward trust certificate during SSL forward proxy decryption. To create a forward untrust certificate, generate a new certificate on the firewall. This certificate should not be trusted by SSL clients, but must still have the capability of signing other server certificates. For these reasons, generate a self-signed certificate that is not signed by any SSL client-recognized CA. Also, do not copy this certificate to the SSL client's certificate stores. However, to ensure that this certificate still can sign the server certificates, select the Certificate Authority checkbox. After you have generated the new self-signed certificate, click the certificate to open it in the Certificate Management interface. After the certificate opens, click Forward Untrust Certificate to configure it as a Forward Untrust Certificate. SSL decryption policy rule sets are similar to the other rule sets in PAN-OS software. The rules are parsed from top to bottom, comparing network traffic to each rule. When the traffic matches a particular rule, the actions defined in that rule are taken and no further rules are checked. Not all traffic should be decrypted. Some traffic cannot legally be decrypted depending on local laws and regulations concerning health records, financial records, and other privacy concerns. A decryption profile enables you to perform checks on both decrypted traffic and traffic that you have excluded from decryption. A decryption profile enables you to block sessions using unsupported protocols, cipher suites, or sessions that require SSL client authentication. You can block sessions based on certificate status. For example, a certificate could be expired, be signed by an untrusted CA, have extensions restricting the certificate's use, or have an unknown status. You also can block sessions if the resources to perform decryption are not available, or if a hardware security module, or HSM, is not available to sign certificates. After you create a decryption profile, you attach it to a decryption policy rule. The firewall then enforces the decryption profile settings on traffic matched to the decryption policy rule. Palo Alto Networks firewalls include a default decryption profile that you can use to enforce the basic recommended protocol versions and cipher suites for decrypted traffic. When SSL encrypted traffic first arrives at the firewall, App ID technology initially identifies the application as web browsing. The default ports for the web browsing application are ports 80 and 8080. If a policy rule is configured for the web browsing application and the service is configured as application default, then SSL traffic will never match the policy rule because the default port for SSL is port 443. In the example, however, the Allow Web SSL Traffic Rule service is configured for Service HTTP and Service HTTPS rather than for Application Default. Any SSL traffic initially identified as web browsing will match this policy rule because the two services are predefined for TCP ports 80, 8080, and 443. After the firewall initially allows the SSL traffic, App ID technology will further identify the traffic as SSL. Once the traffic has been identified as SSL, then the Allow SSL Traffic rule will allow the traffic. SSL Inbound Inspection. The Palo Alto Network's firewall can inspect inbound SSL traffic for potential threats from external hosts to internal SSL servers. After the inbound traffic has been decrypted and the underlying application and data are exposed, the session can be controlled by security policy rules and security profiles. Before the firewall can inspect SSL traffic going to an internal server, it needs a copy of the server certificate and private key. An SSL decryption policy rule also must be configured on the firewall to inspect the inbound traffic. After this configuration is complete, the firewall can decrypt and read the traffic before it forwards the traffic to the server. Assuming that the firewall does not block the traffic, it forwards the original encrypted traffic to the internal server. The secure SSL connection remains between the SSL client system and the internal SSL server. Creating an SSL inbound inspection policy is a two-step process with an optional third step. The first step is to import the internal server certificate and private key into the firewall, which enables the firewall to decrypt and inspect traffic going to the internal server. The second step in the configuration of an SSL inbound inspection policy is to create the actual decryption policy rule. You can specify a source zone and IP address, a destination zone and IP address, and a protocol, port, and URL category. Be sure that the destination IP address includes the IP address of the internal server. On the Options tab, select Decrypt and choose SSL Inbound Inspection. For the certificate field, choose the name of the internal server certificate that was imported into the firewall. An optional third step is to create a decryption profile. A decryption profile enables you to perform checks on both decrypted traffic and traffic that you have excluded from decryption. SSL inbound inspection uses fewer resources than SSL forward proxy, but each firewall model has a supported limit to the number of imported certificates. Other decryption topics. Applications use various degrees of SSL for tunneling, privacy, and authentication. Unfortunately, some are not implemented to standards or use capabilities in the standards that are not compatible with Palo Alto Network's SSL decryption capability. SSL decryption also cannot be used when servers require client-side certificates. When you first implement SSL decryption, you should use a targeted approach to avoid breaking applications that cannot be successfully decrypted. More aggressive policies can be implemented after the base policy is in place and the full range of applications on the network is known. When the firewall detects that a session has been broken as a result of the decryption process, it caches the session information, and it does not decrypt the next session from that host to the same website. Decryption to that website is not attempted again for 12 hours after the first occurrence. After 12 hours, the firewall attempts to decrypt the traffic from that website again. If decryption again fails, the website is re-added to the cache and the process starts all over. To view websites that have been cached for 12 hours, use the following CLI command. Show system setting SSL decrypt exclude cache. The command output also includes the reason that decryption failed: apt, unsupported, non-RFC compliant applications; cert unsupported, certificate manually added or exempted; SSL unsupported, unsupported client certificate, or blowfish. Starting with Pan OS 8.0, you have centralized management for decryption exclusions. You can view predefined decryption exclusions that identify applications that decryption is known to break. Updates and additions to the predefined decryption exclusion list are delivered to the firewall in content updates and are enabled by default. You can also create custom decryption exclusions based on host name. Host names are compared against the server name indication, or SNI, the client requests, or the common name, CN, presented in the server certificate. When the host name matches either the SNI or the CN, all traffic originated from or destined to that server is exempt from decryption. To view the list of websites excluded from decryption, browse to Device, Certificate Management, SSL Decryption Exclusion. To add a website, click Add. The hostname field accepts the asterisk wildcard character. In the example, any website in the somedomain.somewhere domain will be excluded from decryption. To disable or enable individual exclusions, deselect or select the checkbox in the right side column. To disable or enable multiple exclusions at a time, select multiple exclusion entries using the checkbox in the left side column, and then click Disable or Enable. Palo Alto Networks removes decryption exclusions when they become obsolete. However, if a predefined decryption exclusion is disabled, it is not automatically removed from the list. Select Show Obsoletes to check if there are disabled, predefined exclusions on your list that Palo Alto Networks has determined are no longer needed. Even if the decryption policy rule action is no decrypt, the decryption profile attached to the rule can still be configured to block sessions with expired or untrusted certificates. To check certificates, click the No Decryption tab in the decryption profile and select the desired checkboxes. Selection of Block Sessions with Expired Certificates terminates the SSL connection if the server certificate is expired. This action prevents a user from being able to accept an expired certificate and continue with an SSL session. Selecting Block Sessions with Untrusted Issuers terminates the SSL session if the server certificate issuer is untrusted. The traffic log records entries for terminated sessions. To perform these certificate checks, the firewall must still act as an SSL proxy, even though the application data is not decrypted. The traffic log for the session will include a decrypted flag, but the application will be listed as SSL instead of web browsing or an actual application name. The decryption port mirroring feature enables a firewall to forward packet captures of decrypted traffic to a traffic collection tool, such as NetWitness or Solera, for archiving and analysis. This feature is necessary for organizations that require comprehensive data capture for forensic and historical purposes or to enhance DLP functionality. The decryption port mirroring feature is available only on the PA3000 series, PA5000 series, and PA7000 series platforms, and requires a free PAN-PA Decrypt license to be installed to enable it. This free license is perpetual with no expiration date and can be requested from the support portal at support.paloaltonetworks.com. An HSM is a physical device that generates, stores, and manages digital keys. It provides logical and physical protection of the firewall's private keys from unauthorized use and potential adversaries. Use dedicated HSMs to manage the certificate signing functions for SSL forward proxy, SSL inbound inspection, and master key storage functions. HSM support generally is required when FIPS 140-2 Level 3 protection for CA keys is required. Palo Alto Networks firewalls can be used with the SafeNet Luna SA 5.2.1 or later and Thales EnShield Connect 11.62 or later HSMs. HSM use is supported on the PA3000 series, PA5000 series, PA7000 series, and VM series firewalls. It also is supported on the Panorama M100 and M500 appliances and on the Panorama VM. HSM can be used with Palo Alto Networks devices for secure certificate signing in an SSL forward proxy deployment, in secure session key decryption in an SSL inbound inspection deployment, and in secure decryption of master keys. Each firewall maintains a default master key that is used to encrypt its private keys, session keys used in asymmetric encryption, and locally stored passwords. To increase the level of master key security, you change the default master key on each firewall and encrypt the master key with a wrapping key that resides on an HSM. You can use the traffic log to determine whether SSL sessions are being decrypted. If the log entry contains a packet capture, the packet capture will be encrypted because packet capture occurs before decryption. You can also search for decryption traffic by using the log filter. Flags has SSL proxy. SSL sessions can be terminated for a number of reasons, which might include expired server certificates, unsupported ciphers or protocol versions, untrusted certificate issuers, and unknown certificate status and SSL timeout events. SSH decryption can be terminated because of unsupported SSH algorithms. The traffic log records the start and end of each session. The word end in the type column indicates a log entry for the end of the session. The session end reason column records why a session ended. You can use the session end reason filter values to specifically filter the list of sessions to display only sessions that ended because of problems specific to SSL.